So now we get the lesson you've anxiously been waiting for ever since you did that annoying rates of change limits homework, right? Not super fun to do the derivatives with that f of x plus h minus f of x over h as h goes to 0 stuff. That's annoying, right? But luckily we have these shortcut rules, and they're pretty awesome. Let's learn them. Again, I'm not going to read it to you. You can pause. You can read. I'm not gonna. But here, though, I will point out there's lots of different ways that you're going to see the derivative notated. We talked to think about the prime notation last time. So anytime you see a little apostrophe, that's not a typo. That just means derivative. Like f prime of x, that just means the derivative of f. Or y prime, that means the derivative of y. Or dy dx, remember slope, you have delta y over delta x. The delta is really the more geometric notation that stands for the change over an interval. As far as the calculus notation is concerned, we don't want the change over an interval, secant. We want the change at just one instantaneous point. So instead of using the delta symbol that looks like a triangle, they use the d, right? So dy dx, that's the instantaneous rate of change of y with respect to the instantaneous change of x, right? So it's like the slope, but instead of an interval delta, it's at an instant, the d. And then you also see that last one, d dx. That is actually a command that is telling you to take the derivative of that f of x function. So lots of different notations. Most of the time, we'll be using the prime. The process of taking a derivative is called differentiation. And we say that a function is differentiable if you can take the derivative, right? So differentiation, differentiable, derivative, lots of different words. That's okay, though. Here's some rules, right? Let's go for them. Remember, your derivative, it's the slope of the graph at any specific point, right? The derivative tells me the instantaneous rate of change, the slope at a single point. Let's look at these rules. If y equals c, then y prime, the derivative, equals 0. So that is telling you the derivative of any constant is 0. And that should make sense. Think about if you had a function that was y equals 3. It would be a horizontal line 3 units above the x-axis. What's the slope of any horizontal line? 0, right? Any constant, whether it be 3 or whether it be 300 or whether it be 9001 or anything negative even, it doesn't matter. Or it could be something weirder like pi. The graph of any constant would be a horizontal line, and then the slope of a horizontal line is 0. So the derivative of any constant is 0, right? Pretty nice, pretty easy. Derivative of constant, 0. Super nice. The power rule. Okay, now if you're interested in the proof of this rule, you can look it up. It's actually pretty interesting. It uses binomial theorem. You have to expand it, all sorts of stuff, using that limit definition of the x plus h's. Maybe if we have time, maybe I'll walk through with you guys to show you how it's done. Or you can YouTube it on your own. I don't know. It's not important that you know how to prove the rule. It's just important that you can do the rule. And here's just some examples. We have if your original function is x to the 7th, the derivative would be 7x to the 6th. Or if your original, let's say, was y equals x to the 11th, then your derivative would be 11x to the 10th. Or if your original was, how about x cubed, then your derivative would be 3x squared, right? You see the pattern? That number, the exponent, it multiplies down to the front, and then it decreases by 1. So there's your pattern. If you have any power terms, you have x to any exponent, then the derivative, this exponent multiplies down to the front, and then your exponent decreases by 1, right? It's really nice, really easy. 2 steps. That exponent multiplies down to the front, and then it decreases by 1. The derivative should always be 1 degree less if you're working with a polynomial or if you're working with just these algebraic power terms. Okay, now this next one, example 3, it says if you have a coefficient, so if you have some constant out in front of a function, like here, right, you have 7. Well, we know the derivative of x squared would be 2x, and then you could just have that 2x times the 7 that was already there, so it gets you the 14. So really this third rule isn't really something new. It kind of, you can combine it with the previous rule. If you have a coefficient, well, that exponent is just going to multiply down, and it's going to combine with the coefficient that was already there, right? So that's fine. If I had an original function that was like 10x to the 6th, then your derivative would be 60, right? 6 times the 10 that was already there, 60x to the 5th, and then that exponent. Don't forget to decrease it by 1. And then the last one, sum and difference rule. This is pretty easy. If you have if you have addition or subtraction between different chunks of this function, so if you have like a polynomial, or if you have just any other terms that have multiple addition or subtraction between them, it's really no problem. You just take the derivative of each piece individually, and then you just add them and you subtract them together. So you just deal with each piece by its own, and then you're going to be fine. Now, multiplication and division, that's going to be harder, okay? And we're going to have specific rules that teach us how to deal with taking the derivative when you have multiplication between the variables. And we're going to have another rule that teaches us how to do the derivative whenever you have division between the variables in your function. And also, we can deal with composite functions. Also, we can take the derivative of those. We're just kind of starting with the easiest types of functions, the easiest types of derivatives, and then we're going to practice with these for like a week or two, and then eventually we're going to pick up and we're going to learn some of those harder skills, such as the product rule for multiplication, the quotient rule for the division, and then something called the chain rule, which is how we can do the derivative for composite functions. But don't worry about those yet. We're dealing with fairly easy things. Addition and subtraction is pretty nice. You just take the derivatives of each piece, and then you add them or subtract them together based on the operators that were there, right? So here we go. If you had 3x to the 4th, we know the derivative of that, 4 times 3 would be 12. Decrease the power by 1. So you just take the derivative of this piece, how wonderful, and then the derivative of this piece is 7. Now, if you need help with that constant, right, you could always think, like here, let me just do some other linear function. Like if I had y, I don't know why I put the equal sign to the left of the y. That was weird. If you had something like y equals 3x plus 4, right? Slope-intercept form, you know the slope of that line is 3, the y-intercept of that line is 4. Really, the constant doesn't matter. Because remember, when you take the derivative of the constant, it's just going to go away, right? And so it really doesn't matter. Now, the derivative of 3x, it's going to be 3. Now, you can use the power rule if you want, because for something like 3x, you could rewrite that as 3x to the first. Now, that 1 multiplies to the front, 3 times 1, so that'd be 3. And then 1 minus 1 would be 0. So if you wanted to use the power rule, you could. The 1 multiplies to the front, decreases, but then 3 and then x to the 0 power, that's just 1. Right, so you just end up with the 3. You really don't need to do that, though. Just think to yourself, if your function is linear, linear functions don't change slope, right? Lines always have the same slope. It never changes, right? That's why it's straight. And you can always tell what the slope is. It's just the coefficient of the x. So taking the derivative of something like negative 7x is easy. Just cover up the x, it's the negative 7. Or if you had something like 17x, the derivative would just be 17. Or if you had something like negative 9x, the derivative would be negative 9. You know what the slope is for a linear function. It's just the coefficient of the x. And then if you wanted to rewrite it and do your power rule, that's okay. The 1 multiplies down, great, and then it decreases, and then you have your x to the 0 power, which is just 1. So don't freak out about those. Alrighty, let's do some examples, and then I think we're going to probably fly through this notes. It's going to be so fast to take derivatives, much better. Like imagine trying to do that 5 and then x plus h cubed plus 7 x plus h. Oh my God, why would we have a decimal as an exponent? Please change that to 5/2. Imagine having 7 and then x plus h to the 5/2 power, then minus 3 x plus h plus 1. That would only just be the top left chunk. I also don't know why that's there. That would only be the top left chunk of your difference quotient. Then you'd have to subtract your original function. It's all divided by h. You'd have to do all sorts of crazy algebra. It'll work if you do it that way. It's just so much more work. The power rule is much faster. Okay, so let's go for it. Here we go. That 3 multiplies to the front, and then it's going to decrease by 1. Lovely. Next one, you have 7, and then this 5/2 is going to multiply to the front. So here we go, 35 over 2. And then let's see, can I do subtraction with with some fractions. Let's think about it. That's 5 over 2. 5 over 2 minus 1. 1 would be 2 over 2. 5 minus 2. Oh, 3 over 2. Okay. So if you had 2.5 and you subtracted 1, it's 1.5. The fraction exponents are just so much nicer, right? So this multiplies to the front. That builds into the coefficient that was already there. And then subtracting 1 from your fractions, hopefully that's doable. And then the derivative of negative 3x is negative 3. And the derivative of the 1 is 0. You don't have to write plus 0 at the end. So there you go. Much, much, much faster than doing it the limit way. All right, let's look at the next one. I'm going to kind of skip down and do it down here so there's a little bit more room. Here we go. 3t squared. Doesn't matter if it's x's or t's. Who cares? Doesn't matter. 2 times 3, so that's 6t to the first power. Remember, this would be y prime for your derivative. So it would be 6t. Ooh, here we go. Now, you could actually rewrite this. Let's kind of rewrite it here for a second. 3t squared minus, you could rewrite this second chunk as 1/2 t to the negative second power. Since it's t squared on the bottom, that means it's t to the negative second power. So you probably want to rewrite it as a power term before you do the power rule. If you can just get straight to the answer, that's okay. But it may help to split it up and to rewrite it first and then to do the derivative. But anyways, this negative 2 is going to multiply to the front. Negative 1/2 times negative 2. I think that's going to end up being a positive 1. So plus 1. I'm not going to write the 1 for the coefficient. I guess you can if you want. And now be careful when you subtract 1. Negative 2 minus 1 is not negative 1, right? If you have a negative number and you subtract 1, the results should be more negative. So this new exponent should be negative 3. Right, negative 2 minus 1 is negative 3. If you wanted to make it look visually like how the original question was, you could rewrite it as 6t plus 1 over t cubed. Right, t to the negative third power, that's the same thing as having a t cubed on the bottom. Those are interchangeable. I don't care. I don't care. Whatever makes you feel all warm and fuzzy. Next one. Again, you probably want to, instead of having this awful fifth root of x squared, instead of having that very atrocious looking term, just rewrite it as a power term. And then the derivative is going to be much simpler. So I have that coefficient 5. Now you have x squared, and then you have a fifth root. The fifth root is a 1/5 power. So it's really x squared. I think it's a squared. Yep, x squared, and then to the 1/5. So that's 5x to the 2/5. Since it was x squared, there's a 2 on top. Since it was a fifth root, 5 on the bottom, right? A cube root would be a 1/3. Square root would be a 1/2. 17th root would be a 1 over 17, right? Any nth root is just your 1 over n as an exponent. And then you have your minus 4x to the negative first. Plus, okay, you could write 2 to the 1/2 if you want. It's not really going to matter, though. Let's see. Here we go. Z prime, taking the derivative. 2/5 multiplies to the front. 2/5 times 5 would be 2. And then let's see. 2/5 minus 1. Type into your calculator if you don't know how to do subtraction in your head. Subtracting 1, by the way, is never hard and should never be hard in any situation, in any circumstance, ever. But be careful, you're never going to make as many mistakes subtracting 1 or later on adding 1 as you will in a typical Calculus 1 course. So just be careful. 2/5 minus 1 would be negative 3/5. Right? Be extra careful for those fractions that are slightly positive, and then when you subtract the 1, they now are negative. Right? A lot of the times students will mess up with those. Here we go, next one. Negative 1 multiplies, so you're going to have plus 4x to the negative 2, and then, ooh, that's a number, and remember the derivative of any constant is 0. They're trying to trick you, but the derivative of x, or 2 to the 1/2 power, square root of 2, that's a constant, so the derivative of it is 0. There you go. And if you wanted to rewrite it, you could 2 over x to the 3/5. Or if you wanted to, you could put x cubed, and then you could go back to having that ugly fifth root out in front. I really wouldn't. I would leave it as x to the 3/5 on the bottom if you really wanted to do anything. So you could rewrite it like this, or you could have it with the negative exponents. Honestly, I don't really care. If the question specifically tells you not to have negative exponents, then sure, move the stuff to the bottom and make the exponents positive. I would really try to avoid writing it as a fifth root, because that's just, Don't. It's just nasty. One other thing, I want to do one more, just for fun, right? If your original function was, how about pi to the third power? Really common mistake is students will do this. 3 pi squared. You start to use the power rule on something that's not a power term, right? Pi cubed looks like the 3 is going to multiply to the front and then decrease by 1. Nope. You have to remember that pi is a number. So pi cubed is also just some other number. So the derivative of pi cubed is 0, right? Pi cubed is just some constant. The derivative is 0. It would be the same thing if you had a function that was like e to the 5th power. Remember, e is a number, about 2.7. The derivative of e to the 5th is not 5e to the 4th. No. The derivative is 0, right? The derivative of any constant is 0, even if sometimes they try to trick you. Just remember, the derivative of any constant is always 0. Any constant is going to give you a horizontal line for the graph, and the slope of any horizontal line at any point is always 0. Okay, here we go. Remember last time we found some equation of tangent lines? We were thinking about point slope form. Oh, cool. Here, I actually have a proof. I didn't know I had this. It was on the back of my page on the notes. So here's your proof for the power rule. I'm not going to walk you through it. You can pause it. You can watch it if you want. Generally, though, it's just taking a very arbitrary term, right? Any x to the nth power. So you have x plus h to the n, x to the n, and then you end up expanding this using binomial theorem, and then some stuff cancels, then some stuff reduces. You end up getting this, right? You can pause it, and you can look at it. Sorry, the lighting's kind of bad. I'm trying to block the window. Maybe. Anyways, you can pause it. Hopefully, you can read it if you want. But there's your proof for the power rule. All right, remember last time, though, we talked about finding the slope of a tangent line. Y minus y1 equals m, x minus x1. There is your point slope version of a line. That's typically what we want. Here is kind of that same end destination. To find the y-coordinate, all you do is you take your x value and you plug it into the original function. So here, that's what it's telling you to do. Take your x value, a, plug it into the original function. And then to find the m, the slope of the graph at any point, we had to do that instantaneous rate of change. We had to do that limit process before. Well, now we don't. Now we have the shortcut rules. So now I'm just going to take the derivative, and then I can plug my x value into the derivative, and then that is how you get the m. All right, so these are going to be much faster now. Let's go for it. Find the equation of the line tangent to this graph at x equals 1. Sketch the graph and the tangent line. I may just use the calculator. I don't know if I'm going to sketch it, but whatever. Here we go. Let's find the derivative. Let's kind of start where we want. Right? Y minus y1 equals m x minus x1. Right? I know that is my answer. So let's go for it. 1 is the x value. And then let's plug in 1 to the original function to find the y-coordinate. So f of 1, you'd have 2, 1 cubed minus 2, 1 squared plus 1. Okay, so that's 2 minus 2 plus 1 equals 1. Okay, so the point right here is 1, 1. How lovely. So the y-coordinate is 1. That y-coordinate is what plugs in here. And then you need to find the derivative and then plug 1 into the derivative to find the number that goes here. All right, let's do it. The derivative of this first term, I think, is looking like a 6x squared. Remember that 3 multiplies to the front, then it decreases by 1. Now the next term, 2 times 2 would be 4x, and then the derivative of the 1 is 0. So there's my derivative function. This is the equation that'll tell you the slope of any graph at any point. Or really, I guess that's just the slope of that specific graph. And then I specifically also just want to know the slope when x is 1. So let's evaluate the derivative at 1. So we're going to have 6 minus 4. So it looks like we got 2. Okay, plug that number in right there, and you're done. If you wanted to get it into slope-intercept form, all you would have to do is distribute the slope, take that 2 and multiply it into the parentheses, and then you could add the 1 over. I'm thinking that if you get that, what you should get a 2x, that's a minus 2, plus it over. So I'm thinking you're going to end up getting 2x minus 1. You don't have to do that extra work unless the question specifically tells you to. Leaving it in point slope is going to be okay. If you wanted to get it into slope intercept, it shouldn't be very hard, but we know sometimes we make silly mistakes. Even in stuff that's not very hard. So I would recommend stopping with point slope unless you have to, right? Doing the last two steps, it isn't hard, but not doing it is easier. Let's graph it. I don't want to do the work on the paper. Let's just graph it. Here we go. 2x cubed minus 2x squared plus 1. There's your original function. You will need to put it into slope intercept if you're going to use the calculator and be lazy like me. 2x minus 1. Let's graph it and see what we can see. There's that cubic function. There's your tangent line. Now the tangent line does end up intersecting the graph again. Yeah, that's okay. But really, we care about it being a tangent just right in that little local area where it's going to kind of graze the function. Right, so it does happen to kind of come over here and collateral damage. It hits the function again. That's okay. We're really concerning right in that area. Is it going to hit once or twice? Because remember, we're not really caring about the slope between those 2 points. We were only looking at the slope at that one singular point. Let's zoom it in. Zoom box is a cool little trick if you've never done it before. Let's do a zoom box. Click on one corner, drag over and sideways, or if you want, you can go sideways then down, and it just kind of zooms in like it would if you kind of imagined it. So there's your cubic function. There goes your tangent line, right? It looks like that tangent line does just touch it at that one point. Again, it does have the collateral hit over here. That's okay. It just grazes the function right here at the point 1, 1. I guess it's like right here. All right, neat. So yeah, I hope that's pretty okay. Much easier to do with the derivative rules than in that limit way. Okay, anything else on this page? No. Okay, last one. Actually, yeah, last one, I guess. The population of a fire ant colony is growing. Sorry, it's not on the screen. My bad. The population of a fire ant colony is growing according to this function n of t. Where t is measured in days, what is the rate of change of the population with respect to time? So look at that. It's asking you to find the derivative. Remember, rate of change, that just means slope, but it says find the slope at that one instant. So it says find the derivative at time equals 4, right? Gives you the context of the word problem. That's okay. You don't really need it. Just kind of see the math through the word problem. Rate of change means slope. It tells me take the derivative with respect to t, because t is my variable, and then plug in time equals 4. Give units and interpret the answer. All right, cool. Of course, we have, if your original function is n, then n prime, you could also write as dn dt. Both of those are equivalent notations for the derivative. Specifically, that one is Leibniz notation. He preferred the d whatever over d whatever, whereas I think Newton kind of liked the apostrophes. Well, it doesn't really matter, to each his own. All right, so it says find the derivative, and then it's plug in 4. That's not too bad. Here we go. I'm going to rewrite that original function so that it's more like a power term. So I've got 100, and then I've got t. Think about it for a second. If you've got the square root of t cubed, it's going to be a rational exponent. The 3 is going to be on the top, 2 on the bottom, right? Square root of t cubed is t to the 3/2 power plus 1,000. So now I can go through and I can take the derivative. That 3/2 is going to multiply it to the front. Let's see, that would be 300 divided by 2, so then that would be 150. Don't forget to subtract 1 from the exponent. 3/2 minus 1 would be 1/2. The derivative of the 1,000 is 0. Right, so here is your derivative function. If you wanted to, you could rewrite it as 150 square root of t. And then we wanted to plug in 4. I don't know why I put the parentheses. That was totally unnecessary. Square root of 4 is 2. 2 times 150 is 300. Okay, so we've got the derivative, the numerical value. Let's think about the units, right? If you had the derivative, you'd have the rate of change of n, so the population, so you need units of n, which for us would be population of ants, and then units for time, which I think for us was, where was it? Days. There it was. Took me a while. Okay, so here we go. Units on this answer. The population, the units would be ants, and then per day. 300 ants per day. And then let's go ahead and interpret it, right? I know, just as a little side note, if the derivative is positive, that means your original function is increasing. We talked about that last time. If your derivative is negative, that means your original function is decreasing. And if your derivative is 0, that means your original function is constant. Right? We know all those things. And that logic works both ways. If the function is increasing, then you know the derivative, the slope, was positive. If the function is decreasing, you know the derivative is negative. If it's constant, then you know the derivative is 0, right? That logic works both ways. If you know about the derivative, that tells you about the original function. If you know about the original function, that tells you about the derivative. How wonderful. Our answer was positive, so let's think about it. dn dt was greater than 0. Therefore, the population, can't spell, I need a U, population of ants is increasing. Because it's positive, that population of ants is increasing at a rate of 300 ants per day when time equals the 4th day. 4th day, I don't know. Days, I don't know. I don't know if you should put the S at the end. I don't know. Doesn't matter. At that one specific moment. Like, you're not always gaining 300 ants a day. All I know is at that one specific moment in time, at the 4th day, that population is growing by a rate of 300 ants per day. All right, I think that's it. Cool. That's it.